Crisis of cosmology? Have you heard about it? What do you know about it? Hubble tension? Anomalies in the CMB? This is only what lies on the surface of this problem. But what do you know about what really allows you to call it a real crisis? And how does this relate to the evolution of galaxies? And why will there be a revolution in cosmology in the coming years? You will find out about all this if you continue watching. The topic of this video covers a very wide range of subtopics. And if everything is explained in detail, then the information is enough for a whole book. Therefore, in order to not stretch the video too much and in order to not confuse you, some information will be presented in a simplified, in general terms. To people not familiar with the essence of the issue, it may seem that theories of the origin and evolution of galaxies describe well and are consistent with observations, because whole scientific world is working on these models. And as a rule, popular science sources describe only one side of this issue, giving an idealized description. And if you look at this issue only superficially, then everything looks exactly like that. But if you dig deeper, you will find another side of this issue, inconsistencies and anomalies that contradict models and theories of galaxy formation. And some of these anomalies challenge modern physics. And if these inconsistencies do not have a rational explanation, then probably yes, this approach is justified and you should not pay attention to them. But if there are explanations, then this is a completely different matter. And only modern telescopes give clues on how this all can be explained. But to describe this picture, another theoretical basis is needed. We need another theory that will serve as a basis. And this video is dedicated to these explanations. To understand the content of this video, it's necessary to talk a little about the types, properties, and characteristics of galaxies, and about how modern science describes the mechanisms of galaxy formation. Perhaps it will seem boring and uninteresting to someone, but all this information is very important, and almost everything that will be said in first part of the video, in the final part of the video, will be connected in a big common puzzle. Spiral galaxies. Spiral galaxies have a large disk subsystem that has a spiral pattern called spiral arms. There are many young stars in the disk of spiral galaxies, and many very young stars in the spiral arms. According to the pattern, spiral galaxies are divided into a clear, contrasting, grand design spiral pattern, and a spiral pattern that is not clear, and sometimes discontinuous, flocculent spiral pattern. In addition, there is also a subspecies of galaxies, the pattern of which is multi-arm. That is, the total number of arms is more than 2. The straight part of the spiral pattern is called a bar. And here I will explain a very important thing. The fact is that many people do not understand how this pattern is arranged regarding the rotation of the stellar disk. The spiral pattern moves in the same direction as the stars in the disk, but closer to the center it lags behind the movement of stars, and at the edges it moves faster than stars. And another very important point, the spiral pattern has a constant angular velocity, that is, it persists over time. This movement is called rigid body rotation. Any other rotational motion with different angular velocities is called differential. And the stellar disk rotates differentially. That is, the stars revolving around the center of the galaxy are constantly changing their position relative to each other. Thus, if the spiral pattern were due only to the presence of young bright stars, then after a few turns it would be blurred and would lose its initial appearance. Scientists explain the presence of a spiral pattern by density waves, that is, the stars moving in the disk, and create so-called Lindblad resonance. As a result, a stable spiral pattern with an increased density of stars is formed in the galaxy. In turn, the increase in the density of stars by its gravity increases the density of the gas. And in the regions of condensed natural gas, star formation occurs. Spiral galaxies in the near universe account for 60 to 70% of the total number of galaxies, and about the same proportion of barred galaxies of the total number of spiral galaxies. And about 60% of spiral galaxies are flocculent, and the rest are grand design. Initially, it was not clear how spiral galaxies are formed. And the problem is that spiral galaxies have halos and bulges, which are kinematically very different from the disk. The rotation of the disk has a high speed, but the halo and bulge are almost without rotation. Therefore, it's not possible to form a spiral galaxy from a single protogalactic cloud. In addition, studies have shown that with such rates of star formation that we observe in spiral galaxies, the amount of gas that exists in galaxies is only enough for 1 or 2 billion years, which strongly contradicts our observations. In the universe, we see spiral galaxies with very young stars in the disk, and these stars have a continuous age gradient of several billion years. In other words, spiral galaxies look like they have been forming stars continuously for many billions of years. And even if we imagine that external gas enters galaxies by merging with small satellite galaxies, then in this case, this gas would be enough for only 1 billion years. But all the satellite galaxies would be absorbed. And to explain the observations, we need a constant inflow of gas that would feed the process of star formation in the disk. In addition, a factor has entered the scene of cosmology that cannot be ignored in models of galaxy formation. This is dark matter. Therefore, it becomes necessary to explain the mechanism of formation of spiral galaxies, taking into account these two factors. In the lambda-CDM model of cosmology, that is the model of cosmology that takes into account cold dark matter, clumps of dark matter first combine to form a common halo. Accordingly, the probability is very high that as a result of such mergers, the resulting halo will have an angular momentum, that is rotation. The gas, under the influence of the gravity of the dark halo, thickens and forms stars. Later, gas from filaments that flow into the galaxy swirls along with the dark halo and creates stars in the disk. And this flow continues and feeds the disk with fresh gas for star formation. Elliptical galaxies. Elliptical galaxies have different shapes, from completely spherical shape to an elongated elliptical, which can sometimes look almost like a disk. A characteristic property of elliptical galaxies is that on average these galaxies have old stars and accordingly either slow or completely absent star formation. Therefore, they are usually red and faint. A distinctive feature of this type of galaxies is that the most giant and massive galaxies are elliptical. The lightest and most compact are also elliptical, while spiral galaxies are mostly medium masses. Initially, it was assumed that they are formed by the collapse of the primordial gas, that is, by the gravitational collapse of a gas cloud followed by the formation of stars. But in more recent models, they are formed by merging galaxies, mostly from the merger of disk galaxies. Lenticular galaxies. By coincidence, this type of galaxies combines two subspecies with different evolutionary histories. The first, galaxies that are transitional between ellipticals and spirals. And second, these are spiral galaxies in which, for unknown reasons, star formation has ceased. Either star formation doesn't occur in the entire disk, but in the ring. That is, in them, instead of spiral pattern with star formation, there are rings with star formation. And in those galaxies in which there is almost no star formation, the gas kinematics are often disturbed. Some galaxies have a gaseous disks that are tilted relative to the stellar disk. In some lenticular galaxies, there are nuclear polar disks. There are galaxies with polar rings. And there are galaxies in which the gas rotates in the opposite direction to the stars. Due to the fact that lenticular galaxies almost do not differ geometrically from spiral galaxies, a hypothesis has been proposed that lenticular galaxies are spiral galaxies, devoid of gas. There are suggestions that the filaments that feed spiral galaxies either stop feeding the disk with gas, or do it at an angle. the gas stops flowing into the disk and star formation stops or slows down. In galaxy clusters, the proportion of lenticular is greater than outside of clusters. And we see that the proportion of lenticular galaxies is increasing over time, especially in clusters. Both types of galaxies, elliptical and lenticular, belong to the early type of galaxies, and spiral galaxies belong to the late type of galaxies. There is also a type of irregular galaxies. These are galaxies that do not have symmetry, and the kinematics in which is very disturbed. The hierarchical concept of galaxy formation is part of the lambda CDM cosmology. This concept implies that large galaxies and cosmic structures were created by merging smaller ones. That is, small galaxies merged and formed large galaxies. Galaxies combined into small clusters, and small clusters of galaxies merged and formed larger clusters, and so on. Among the galaxies of all morphological types and of all sizes and masses, there are galaxies with active nuclei. Galaxies with active nuclei include quasars, blazars, radio galaxies, Seyfert galaxies, laser teeths, and linear galaxies. All these objects have a common feature: an active core. The activity of the nucleus manifests itself in a strong radiation in different ranges, and in the case of quasars, it also throws matter at high speed in the form of jets. All these different names have appeared because historically this activity of the core has been observed in different ways. If the jets move in a plane perpendicular to the line of sight, then such objects are called radio galaxies. If the jet is pointing at us, then in this case it's a blazar, and galaxies whose jets have an intermediate direction are called quasars. Of course, this division is conditional, because all these objects radiate intensely in the radio range, and they can all be called radio galaxies. Seyfert and linear galaxies do not have jets like quasars, but have a lobe-shaped radio-emitting region near the nucleus. Their activity is also manifested in radiation from the high-speed movement of matter in the nucleus. All these objects, according to the radiation energy, are divided into radio loud and radio quiet. For classification, names quasars, Seyfert galaxy type 1 and 2, and galaxy liner are mainly used. Quasars have highest radiation energy of nucleus, and liners have the lowest. Seyferts have an intermediate position. Radiation in the form of a lobe in Seyfert galaxies is called narrow line regions. It's associated with the fact that in this area, supposedly, there is a very weak and short jet. And the radiation near the core of the Seyfert galaxy is called broad line regions. There, the matter moves at a very high speed and has a large dispersion. The researchers explain this movement of matter by the fact that in the core, in the vicinity of the black hole, there must be an accretion disk, in which the matter approaching the black hole is strongly heated and accelerated. Seyfert galaxies that have both of these types of radiation are referred to as type 1 Seyfert, or sometimes they are called type 1 active nuclei. Seyferts without a radiation of broad line are type 2. The best explanation for this division in two subclasses is the unification model, according to which active nuclei of type 1, not obscured, are observed at small angles of inclination, that is, almost face on. Thus, it's possible to see regions with a narrow and broad line, and nuclei of type 2, obscured, are observed at large inclination angles, that is, closer to H-on, so they are observed through large masses of gas and dust. By some properties, all these galaxies with active nuclei have only conditional division, and according to these properties, they have a smooth gradient between them. From one end of this gradient, we see quasars, with huge radiation energy from nucleus and jets in all ranges. And on the other end of this gradient, ordinary galaxies in which the rate of star formation is high. There is also a separate class of galaxies which are characterized by a very bright glow in the infrared range in relation to other radiation ranges. The explanation is that in these galaxies, there is a very large amount of dust, which obscures the radiation, absorbs it, and re-radiates it in the infrared range. The nature of initial radiation is not yet clear, but the researchers suggest two sources. These are burst of star formation or nucleus activity. There is also a version that these galaxies in the process of major merging. There is another very important phenomenon that is present in a very wide range of galaxies, and this is the galactic wind, which often has enough energy to leave the galaxy, and in this case it's called the outflow of matter. Further, I will call it outflow. Outflows are usually associated with star formation, that is, new bright stars create a powerful stellar wind, or supernova explosions create shock waves of matter moving at a great speed. Numerous studies have shown that the outflow has a bipolar direction and a biconical shape, that is, it has a shape of diverging cones across the plane of the galaxy. Moreover, it's the shape of a hollow cone. The researchers came to this conclusion because they found that the frequency of detection of the outflows depends on the angle of inclination of the galaxy. Outflows are very common among galaxies with a high level of star formation, but their properties depend very little on other properties of galaxies. Theoretical models suggest that the velocity of outflows should depend on the rate of star formation, and such a correlation was found. The correlation of outflow velocity with mass of the galaxy was also found. That is, the more massive the galaxy, the higher the outflow velocity, which also fits into the logic. But both of these correlations are not clear, with large deviations. Therefore, the question of what exactly determines the outflow velocity has not yet been resolved. Outflows are common to all morphological types of galaxies, especially for irregular ones. To some extent, the above described origin of galaxies is not devoid of logic and looks quite consistent. But with a detailed study and comparison of theory with observations, one can confidently assert the opposite, that such a vision of the formation of galaxies is wrong. Observations revealed a lot of contradictions with theoretical models, and now we will talk about them. The hierarchical concept of galaxy formation mentioned above implies that giant elliptical galaxies are the product of merging elliptical or disk galaxies, and the mergers of galaxies should lead to a powerful burst of star formation. But studies show that the stars in the center of these galaxies are very old. There have not been any burst of star formation there for the last few billion years. That is, this observation strongly contradicts the hierarchical concept, and this may indicate three ways of explanation the observations. Either giant elliptical galaxies are not formed by merger, or the universe is older and these new stars are already old, or there is a hypothetical error in determining age of stars. In addition, stars in elliptical galaxies and stars in the disk of disk galaxies differ in the type of metallicity. That is, they have a different type of metallicity in terms of the percentage of magnesium and iron. Therefore, elliptical galaxies cannot be the product of a merger of a disk galaxies. Here you need to pay attention to the fact that according to the same concepts, the initial galaxies should be mostly disk galaxies, and therefore elliptical galaxies should be the result of a merger of mostly disk galaxies. In addition, studies show that elliptical and lenticular galaxies are kinematically more similar to the spiral galaxies than to the result of a merger. Thus, it turns out that the evolution of morphological types should tend to increase the proportion of elliptical galaxies and decrease the proportion of disk galaxies, because from almost any merger, a disk galaxy cannot turn out, except for cases when a disk galaxy merges with any small galaxy. But observations suggest the opposite. In early times, the universe was dominated by elliptical galaxies, and in the last few billion years, most of them are already spiral galaxies. The gaseous polar rings and disks in lenticular galaxies which are supposed to consist of incoming filamentary primordial gas, should have very low metallicity. But observations have shown that it's not so. These structures have a high metallicity, which called into question the idea of inflow of external gas. But later, the idea of galactic fountain was proposed, according to which supernova explosions generate winds saturated with heavy elements, which, leaving the galaxy, mix with external gas and saturate it with heavy elements, and later this already mixed gas settles into the galaxy. Exploring lenticular galaxies, researchers are faced with an unsolvable problem. The fact is that, looking into the distance, we see galaxies at different times in the life of our universe, and we see some evolution of spiral galaxies into lenticular ones, especially in clusters. This process of transition occurred about 4 billion years ago. Therefore, in the disks of lenticular galaxies close to us, there must be stars 4 to 5 billion years old. But we see that in 60 to 80% of the cases, the stars in the disk of lenticular galaxies are over 10 billion years old. And in the bulges, the picture is opposite. There are young stars there, in contrast to the disk. And this may indicate two options for solving this issue. Either lenticular galaxies do not evolve from spiral galaxies, or we again have a hint of a hypothetical error in determining the age of stars. In clusters, although the proportion of lenticular galaxies is greater than outside clusters, the proportion of spiral galaxies is still significant. A cluster of galaxies is a number of galaxies that randomly rotate around a common center of mass. And as we remember, there is an assumption that gas in the form of filaments flows into the disk of spiral galaxies and feeds star formation. And due to the chaotic motion of galaxies in cluster, the scenario of filamentary accretion into the disk becomes unlikely or difficult to implement. This is what is associated with the increased fraction of lenticular galaxies in clusters. But accordingly, due to this effect, there should not be spiral galaxies in clusters. But they are there, and there are many of them. There is another controversy regarding the scenario for the formation of disk of galaxies. The filaments flowing into the galaxy acquire angular momentum due to the fact that the dark matter halo has angular momentum. That is, this gas of filaments is swirling because the dark matter halo is rotating. Later, this gas is converted into stars, and thus a stellar disk is created. And if we accept the model of galaxy formation with the rotation of dark matter halo, then polar rotating gas disks, or gas disks that rotate against the rotation of the stellar disk, put us, if not in a dead end, then in a very difficult position, since the halo cannot change its rotation to the opposite or to the polar one. An inflow of external gas is also needed to explain one serious problem. In the conventional theory of star formation, stars form from the interstellar medium, which over time evolves and becomes saturated with heavy elements, which in turn are formed in supernova explosions. Thus, stars that formed in ancient times should have low metallicity, and young stars should have high metallicity. The fact is that after a condensed cloud of gas forms a star, thermonuclear reactions start in it. A stellar wind appears, which blows away nearby clouds of gas and prevents the star from gravitationally absorbing the outside gas. Thus, a star must have the same metallicity as the gas from which it was formed, with the exception of those elements that can be formed in the star. Stars, depending on their mass, can have different lifetime. Heavy stars live their lives quickly, over tens of thousands or millions of years, and light stars live for billions of years. The lifetime of G-dwarfs, to which our Sun belongs, is about 9 billion years. These stars were formed at different times in the life of our galaxy, and accordingly, their metallicity should be very different. But it turned out that they all have the same metallicity, with a variation comparable to the measurement error. This problem in astrophysics is called G-dwarf paradox, or G-dwarf problem. This problem has not been fully explained, and the scientists had to make two assumptions. First, an external gas is needed, which would dilute the internal gas in the disk of the galaxy all the time. Moreover, this gas must flow at such a speed that the metallicity of the gas in the disk would remain constant. And the second assumption: at the time of beginning of the formation of the disk of the galaxy, the metallicity was already quite high, but the reason for this high metallicity could not be explained. The inflow of gas that is needed to form a disk is rarely observed in spiral galaxies, and if it's observed, then its amount is very small to explain the rate of star formation. Also, theoretical models suggest a direct relationship between the inflow of matter and the rate of star formation. And this is the first problem related to gas in spiral galaxies. The second problem is that, according to the same models, the galactic wind or outflow, in terms of the mass of the outflowing matter, should be comparable to the star formation rate. But observations show that the masses of the outflows often exceed the rate of star formation by several times, or even tens of times. And the problem is complicated by the fact that these outflows are observed very often, and their masses are huge, while the inflows of matter are observed very rarely, and their masses are very small. And even today, there is no rational explanation for the properties of these outflows, because in addition to the fact that outflow masses often exceed the star formation rates, the outflow velocity doesn't explicitly depend either on star formation rate or on the mass of galaxies. Outflows are present in galaxies across the entire spectrum of masses and star formation. Also, in theoretical models, there is a lower limit of star formation at which wind appears. And even in our galaxy, with a very low rate of star formation, this galactic wind is present. And even the source of these outflows is still unclear. And this lack of agreement between the observed properties of outflows and theoretical expectations calls into question our understanding of this phenomenon. But the most important surprise for the researchers was that cold, neutral gas was found in these outflows, the streams of which stretched over great distances, and the speed reaches hundreds and thousands kilometers per second. If the hot ionized outflow can be somehow explained by the stellar wind or supernova explosions, then the cold gas flows doubled the problem. Of course, the problem is not so serious. There are researchers who compare the data, make assumptions, and get unacceptable results that suits them. And there are cases in which everything really looks normal. But in general, the problem remains unresolved until now. Various explanations for cold gas flows have been proposed: acceleration by stellar radiation and acceleration of cold gas clouds by hot gas clouds. But even without research, it's clear that under the influence of radiation, cold gas will heat up and ionize. And when you try to accelerate a motionless cloud of cold gas by a fast-moving cloud of hot gas, the cloud of cold gas will simply be destroyed and they will mix, which is exactly what the simulations show. There's one more fact that casts doubt on such an explanation for the acceleration of cold gas. Spiral galaxies have approximately the same content and distribution of cold gas, and if this acceleration mechanism works, then in the outflows of different galaxies, there should be a comparable ratio of the masses of cold gas and hot gas. But in different galaxies, the ratio of the masses of hot gas and cold gas differs by 4 orders of magnitude. That is, it differs by tens of thousands of times. All these oddities give rise to the idea that outflows are based on completely different physical processes. Do you remember? One of the arguments for the need for dark matter was that without dark matter, the gravity of ordinary matter is not enough to quickly begin the formation of galaxies. But in simulations with dark matter, another problem arises. The growth rates of galaxies is higher than necessary. The rates of star formation in them are much higher than those observed in the universe, and galaxies are an order of magnitude more massive. All galaxies suffer from excess mass, especially in the categories of very heavy and very light galaxies. In the simulations, the galaxies are not only overweight, but the stars in them are much younger, in both massive in light galaxies. There is another interesting feature in the universe, which is called the bimodality of galactic properties, which is that very massive galaxies have an old population, and small light galaxies have a young population. And in simulations, there is no such bimodality in the age of stars. And in order to explain these problems, some feedback mechanism is needed that would prevent rapid settling of gas in the galaxy and its rapid growth. Moreover, this mechanism should turn on in massive galaxies at the moment when they are already formed in the universe. It should also slow down the growth of galaxies in other weight categories, exactly in such a way that very young light galaxies and very old massive galaxies are obtained. Presumably, galactic wind is this mechanism, which appears as a result of intensification of star formation and blows away the surrounding gas, and as a result, star formation stops. But the burst of star formation only temporarily restrains the settling of gas. But a mechanism is needed that would act constantly. And besides, despite the huge masses of outflows, there is no evidence that the galactic wind extinguishes star formation. But even activating this feedback mechanism in simulations doesn't allow to obtain a result that would be similar to what we observe in the universe. Even if simulations and star formation observation can be reconciled, a very weak wind is obtained to explain such outflows of mass, especially in light galaxies. The inclusion of additional mechanisms for suppressing star formation entails an even greater complication of agreement with observations. It turns out that this mechanism should be all artificial with many adjustable parameters, which entails the problem of fine-tuning, and such understanding will inevitably lead to the problem of artificiality, the man-made nature of the universe. Therefore, another explanation is needed. For a very long time, it was believed that the reason for the low rate of star formation in elliptical and lenticular galaxies is a very small amount of gas, but studies show that there is gas in them, and in sufficient quantities, both cold and ionized. Its distribution and kinematics are different, but often it's located in the disk. But why in the presence of gas is there almost no star formation? This remains a mystery to this day, and even the source of this gas has not been identified. Besides the mystery of star formation, it has been found that in the center of galaxies, the ratio of star formation rate to the amount of cold gas is very high, as in ultra-bright galaxies, while at the periphery, this ratio is very low, as in ordinary galaxies. That is, as if in the center of galaxies, gas is very willingly transformed into stars, and very reluctantly at the periphery. The inexplicable inefficiency of star formation is also observed in the giant molecular clouds of gas. It's assumed that all stars form in such clouds. Although observations show that only about 5% of the mass of the cloud turns into stars. Also, observations have shown that in the region of the bar, the efficiency of star formation is about 2 times lower than in spiral arms. It has been suggested that stars are more actively formed as a result of the collisions of clouds of cold gas, but these assumptions were not confirmed. But there is evidence to the contrary. In some dwarf galaxies, star formation occurs even when the gas concentration is below the minimum threshold at which star formation should begin. There are other indirect evidence that not everything is so simple in this matter, and many researchers come to the conclusion that the presence of cold gas is not a determining factor in the process of star formation. Some other factor, unknown to us, affects star formation, and it's still a mystery. There is one more inconsistency between the lambda CDM model and reality. In the process of primary nucleosynthesis, all matter in the universe was created, and to date, observations show that there is several times less matter in the universe than models predict. Different studies give slightly different estimates, but we will not talk about this inconsistency further. I just mention it for the sake of completeness. If you are fond of cosmology, astrophysics, or just popular science, then perhaps you have already heard some of these problems. But that's not all the surprises, the rest I will tell you later. There are logical explanations for all these mysteries and inconsistencies. And if you watched the previous video, then you know that the theory of moving space implies an alternative version of evolution of galaxies, which is based on just one difference from the generally accepted paradigm. But this difference completely changed the course of the evolutionary development of galaxies and provides answers to these inconsistencies. And this difference primarily refers to spiral galaxies, namely to the spiral structure. If in the generally accepted picture the spiral pattern represents spiral density waves, then in theory of moving space the spiral pattern is created by gas moving away from the center of the galaxy, from the core itself, from the black hole itself, or from the area immediately close to it, just as matter moves in the jets of a quasar. But the quasar jets do not change position. And imagine what will happen if the quasar starts to rotate. Then the result will be waves of gas flowing out of the core in a spiral. But the classical quasar is not a very good example. The speed of movement in its jets reaches the speed of light. But there are examples of low velocity, low energy jets that are better suited to this role. So, imagine a disk galaxy in which gas flows out of the core at high speed towards the edge of the disk. If the velocity of this gas is sufficiently high, then some part of its trajectory will be straight. That is, it will look like a bar. As it moves, the gas changes speed due to interaction with interstellar gas and other effects. And the trajectory of its movement in a spinning disk begins to describe a spiral structure. And the pattern of this structure will depend on several factors: on the speed of space, on whether space accelerates or slows down in this place, and on whether the movement of the gas has only a radial component of velocity, or there is also a circulation component. And if you watched the previous videos, then you know about the effect of the inertial trap, which doesn't act only on bodies moving in radial direction, and it acts on all bodies that have any other direction of motion except for the radial one. Therefore, it's very important which direction of movement this gas has. But here it's very important to note that the moving gas is almost invisible, and spiral arms are bright luminous areas of the disk. Imagine how a jet of gas is moving at the disk of the galaxy at great speed, and what happens if there is a star in its way. The star has two options. First, take on a portion of the gas. In this case, this gas, which almost entirely consists of hydrogen, will be distributed over the surface, and the star will begin to shine with fresh power, as if it had just been formed. And if you're wondering what provides luminosity of the spiral arms, then you will know that in spiral arms the increased gas content, the high rate of star formation, and the main luminosity of spiral arms are provided by very heavy and very bright stars of class O and B. And now attention! To date, scientists do not know exactly how such massive stars form, and the existence of such stars forced them to reconsider the theoretical models of star formation. The problem is that, as I said earlier, when the cloud of gas thickens and the first thermonuclear reactions are ignited, a stellar wind appears, which blows away the surrounding gas, and after that, the star is not able to increase its mass significantly. The normal mass to ignite these reactions is much less than the mass of our Sun. And in the early stages of our understanding of stellar evolution, the existence of stars with a mass greater than 8 solar masses was considered impossible. But now we know stars with hundreds of solar masses. And the only way to overcome this stellar wind is the kinetic energy of gas clouds. And to date, researchers know about the flow of gas along the spiral arms. And by this movement of gases, they are trying to explain the mystery of the formation of such massive stars. Let's go back to our star and the gas jet. In the second option, the action of the gas jet will lead to what? That's right, to the explosion. And if you're interested, you will find out that most Type 2 supernova explosions happen in spiral arms. And the Type 2 supernova explosions differ from the Type 1 by the presence of hydrogen lines in the spectra. There are other types of supernovae that also occur most often in spiral arms. And so the gas moves to the edge of the disk, igniting and exploding stars. And if its speed is not high, then at a certain distance from the center, it will slow down. And at this point, the spiral pattern will be turned into a ring pattern, which often occur in lenticular galaxies. And if the speed is still high, then the gas will continue to move and go beyond the stellar disk, and the spiral structure will continue there, where there are almost no stars to create density waves. But nevertheless, a spiral pattern of gas is very often observed there. Okay, let's imagine that supernova explosions and the existence of class O and B stars in spiral arms are just coincidence. What direct evidence is there that the gas is moving from the core to the edge of the disk? To see the movement of gas in the thickness of a stellar gas and dust disk is a very difficult or even impossible task. And it's complicated by the fact that at the end of the stellar disk, the gaseous disk continues, and sometimes at the distance of several radii of the stellar disk. And here you need to understand that it's much easier to see the movement of gas in front of the disk, as it's done by observing biconical outflows, than to see its movement inside the disk, just as it's impossible to see the movement behind the disk. But there are a number of evidences about which I will now tell you. But before I get started, I want to explain a little about how the kinematics of stars and gas in galaxies are measured and analyzed. Spectrographs are the main instrument for studying the kinematics of gas and stars in galaxies. These instruments analyze the spectrum and determine the velocity of gases by the Doppler shift of the absorption or emission lines in the spectra. And the radiation of this gas can be noisy by the background radiation of the disk. So there are situations in which it's impossible to determine the movement of the gas. Initially, slit spectrographs were used, which are more often used to measure the rotation curves of galaxies. But slit spectrographs show only the gas kinematics along a narrow line on which the spectrograph slit lies. With the development of technologies, multi-unit spectrographs appeared, which show the kinematics of the gas not in the plane of the slit, but over the entire field of view. And in recent years, the resolution of these spectrographs has reached high results, which make it possible to study gas kinematics in high resolution. Therefore, the authors of early studies, who used old equipment, were deprived of the completeness of information, and their works are not so informative as modern ones. And one more important point. Now you see on the screen a kinematic picture or velocity field, which corresponds to a rotating disk. The approaching part of the disk has a blue shift of the spectrum, and the receding part has a red shift of the spectrum. And this is how the velocity field looks if the movement in the disk occurs from the center outward. In the part of the disk closest to us, the movement will be directed towards us, and accordingly will have a blue shift in the spectrum. And in the far part of the disk, the movement comes from us, and accordingly will have a red shift of the spectrum. And if the motion in the disk is mixed, then the velocity field will also have a mixed form. But if the disk is thick, then rotational motion will dominate in it. There is another difficulty in studying the kinematics of gas. The fact is that we do not see exactly where the gas is directed. The Doppler shift effect only tells us whether the gas is moving towards us or moving away from us. And this is just one of the components of full speed. But the researchers, based on the logic of the interpretation of the phenomenon, built theoretical models of the velocity field and comparing them with observations draw conclusions, whether the interpretation coincides with the observations or not. In some studies, the authors reported that the outflow has such kinematics as if it comes from the edge of the disk, and often these are galaxies with an increased rate of star formation. In addition, the emission of gases, which are typical for outflows, have a bimodal distribution in the galaxy. It is a distribution in the form of a biconical outflow and distribution along the plane of the disk. And this distribution extends over huge distances. For many years, researchers have been trying to prove the concept of inflow of matter into spiral galaxies. To do this, they try to determine the direction of movement of gases outside the disk. But at a great distance from the stellar disk of the galaxy, the gas is almost impossible to track by its radiation. But it's possible to get a very clear signal through the absorption lines in the spectrum of bright radiation passing through this gas. Such a bright source, for example, can serve as a quasar. At the same time, it should be understood that such studies are not very informative, since they do not give us complete information about the speed and direction of the gas, but only the projection of its speed on the line of sight with the quasar. But there is a way to improve the informativeness of such studies. It's necessary to select galaxies with 2 or more quasars in the background. In this case, we will get 2 or more projections of the gas velocity. And these studies have confirmed that the gas outside the disk mainly has a rotation motion, but its kinematics doesn't quite correspond to the rotation of the gas. That is, it's highly likely that the gas has also a radial component. There is one very interesting recent study with very extraordinary results, but we will talk about it another time. The outflow of gas in the disk in half of the cases can be interpreted as a rotation, and in other half of the cases as a counter-rotation. Just in one of the galaxies, the outflow along the plane of the disk was probably mistakenly interpreted as a counter-rotation of the gaseous disk. But the gas has a blue shift with a gradient along the major axis, which the authors interpreted as a possible outflow along the minor semi-axis of the disk. In addition to indirect evidence, there is also a direct observations of the outflow of gas at the edges of the disks. At the same time, galaxies with signs of gas inflows are sometimes found. Sometimes these are inflows from the edges of the disk, and sometimes this is indicated by the movement of gas on the surface of the disk. Undoubtedly, the idea of galactic fountain is not devoid of sense, and some part of the gas, escaping from the region of the nucleus, cools down over time and settles on the disk. But what in the classical understanding of the kinematics of the stars and gas in the galaxy can be interpreted as inflow of gas, in the theory of moving space, it should happen with any gas settling on the disk. Do you remember this picture, which shows the velocity field of space in a disk galaxy? And according to the law of inertia, any body moving from the area with one velocity of space to the area with other velocity of space change its speed relative to the galaxy in such a way that its speed relative to the space doesn't change. Therefore, any gas settling on the disk of the galaxy will acquire additional speed towards to the center of the galaxy. And this is one of the predictions of the theory of moving space. Like it or not, observations of the stars in our galaxy will show. But in order to see the change in the velocity vectors of star crossing the plane of the disk, decades of observations are needed. But we have the opportunity to study the flow of stars belonging to the same stream. There is a group of stars in our galaxy with a common kinematics in the form of a stellar stream. It's called a Sagittarius stream. According to the researchers, this is one of our satellite galaxies, which was torn apart by tidal forces and is now at the stage of merging with our galaxy. And to our luck, it crosses the disk of our galaxy. And precisely at the point of intersection, we see such a shift that the theory of moving space predicts. On the internet, there are several types of images of this stream, and they are very different. But all of them have this shift that researchers associate with the core of this galaxy. There are images in which the Sagittarius stream crosses the disk twice, and there should be a similar shift at the place of the second intersection. But there are images where there is only one intersection of the disk. I can't say exactly which of these images is more true, but I tend to think that the short version is closer to reality. Because in order to stretch to a length 10 times greater than the original size, it's necessary that the speeds of the stars of initially a single object differ significantly. And if it were so, then this object would not retain its structure in the form of a thin flow. Just don't confuse this with the spaghettification effect near the black hole's event horizon. In our case, the conditions completely different. And the images with two intersections are probably made to show the trajectory of the flow. Unfortunately, I didn't have much time to study this phenomenon in detail. Perhaps in the future I will return to this issue. We can test this prediction of the theory not only in our galaxy. As I said earlier, gaseous and stellar polar rings and disks are often found in lenticular galaxies. This is how the curvature of the trajectory of stars or gas crossing the plane of the disk of the galaxy should look like. In the case of the classical gravity, the deflection has an absolutely other form. And this is the kinematic picture that we see at the polar disk in one of the lenticular galaxies. One can of course assume that this is simply a distortion of a disk shape associated with a distorted signal, which can often be found in such images. But you pay attention to the kinematics of the disk, to the field of velocities. It corresponds to the distortion of the velocity field, which should be when crossing the disk plane according to the theory of moving space. But nearby you see a polar disk without this shift, or this effect in it is expressed weakly. Also, it's obvious that the resolution is lower in this image, because this galaxy is much further away from us. In addition, in order to correctly determine this effect, we need to see clearly the contours of the polar disk itself. Unfortunately, there is not much research on the kinematics of the polar disks and rings, but there are a lot of pictures of the galaxies with polar rings. And in images where there are clear contours of the ring itself, this shift is often observed. Okay, let's go back to outflows. Considering all the data, some researchers suggest that the outflows are not caused by starburst, but by active nuclei. But here you need to understand one thing. If jets of gas really move in the disk and refresh old stars with new gas, then the increased star formation itself in galaxies with active nuclei is only a side effect of outflows. In this case, there is no burst of star formation, but only imitation of this process occurs. Of course, the formation of new stars also occurs, but to a lesser extent. And it turns out that outflows do not occur due to increased star formation, but increased star formation occurs due to outflow, and this solves the problem of inflows. To explain this quasi-star formation, there is no need for inflow of external gas. And in general, to explain the formation of the disk, also there is no need for inflow of external gas. And it becomes clear why the masses of outflows sometimes greatly exceed the rate of star formation. But there are two questions. First, where does this matter flowing from the core come from? And the second question, how gas with only radial velocity creates a disk that rotates? Also, there is evidence that that flowing gas also has a tangential velocity component. That is, this outflowing gas rotates. It's possible that the initially emitted gas has a small tangential component, and later most of the radial velocity, due to the effect of inertial trap and possibly some other effects, is converted into tangential velocity. But there is an interesting fact. The disk rotates in the same direction in which the jets are spinning. That is, astronomers, even without measuring the kinematics of stars, determine the direction of rotation of the disk according to the spiral pattern. The only difficulty that exists in this matter is to determine which side of the disk is closer to us and which is further. That is, the direction of rotation of the jets is related to the direction of rotation of the stars in the disk. A lot of what happens in the active core raises questions. Many phenomena are still poorly understood and have no explanation. Active nuclei are full of mysteries. In particular, there is not even an idea how it's possible to accelerate cold gas up to 1000 or more kilometers per second, and that this gas would remain cold at the same time. Modern physics doesn't know such mechanisms. All known mechanisms will lead to ionization and fragmentation of the cloud into small turbulent flows. But in the theory of moving space, this is solved very simply. Presumably, the speed of space in the vicinity of a black hole reaches thousands of kilometers per second, and any matter leaving this area, according to the law of inertia, must maintain its speed relative to space. Therefore, getting into area with a lower speed of space, its speed relative to the center of the galaxy increases. And apparently, the gas flowing in the jets can be both hot and cold. On which it depends is not yet clear. And if so, then this solves the problem of explaining the 4 orders of magnitude spread in the cold gas content in the outflows. Another important question is why the observed outflows are biconical. The shape of the biconical outflow doesn't fit well with the hypothesis of supernovae or stellar wind. Both in the case of supernovae and in the case of stellar wind, the movement of gas occurs isotropically, that is, in all directions from the source, and instead of biconical outflows, we should observe an outflow in a spherical shape. But if we assume the effect of addition, due to the fact that there are many sources of outflow, and they are located in the same plane, then the outflow should have maximum values in the direction perpendicular to the plane of the disk. But if we look at it from the standpoint of the theory of moving space, then we will see that whatever the source of outflows, whether it's gas from supernova explosions or stellar wind, or if a jet of hot gas comes out of the core, this gas can have vertical motion. All these types of flows leaving the disk will acquire additional radial speed, for the same reason, because they move into an area with a different speed of space, and as a result, outgoing vertical flows will have a biconical shape. Sometimes researchers have the idea that the active nucleus is the cause of the high level of ionization and velocity dispersion in the narrow line regions, and that outflows transmit a high level of ionization and velocity dispersion to regions far from core. There is another problem associated with the radiation of the regions with broad line. In the process of research, it turned out that this near-nuclear radiation with a broad line has 2 maxima, 2 peaks, and these 2 peaks have an anomalous asymmetry. The blue shifted peak has a larger offset from the system velocity, that is from the velocity of the motion of galaxy, and the red peak has a larger signal amplitude, and this asymmetry is inherent in most of the observations. And if we try to interpret this asymmetry, it turns out that less gas is moving towards us, but at higher speed, and more gas is moving away from us, but at lower speed. Why is this asymmetry anomalous? Because if this radiation comes from the gas moving in the accretion disk, then this radiation should be more symmetrical. And if the mass in it is really distributed non-uniformly, and most of the disks indeed have asymmetry, then the accretion disk cannot simultaneously be turned towards us by the same side of the asymmetry. That is, even if the problem lies in the asymmetry of the accretion disk, then statistically there should be signals with the opposite effect. And this problem calls into question the model of the radiation of the accretion disk. And the simulations of radiation from an asymmetric accretion disk do not reproduce the observed radiation. The explanation of the cause of this radiation was also greatly complicated by the fact that it is not constant. Its intensity varies greatly, and this, in turn, also contradicts the model of radiation from the accretion disk, which should be more constant without rapid changes. In this regard, a very important question arises. If this radiation comes from an accretion disk, then why is there no similar radiation from the stellar mass black holes, in which jets are observed, but there's no radiation from the accretion disk? And here I will tell you a little about the accretion disk. The body rotating around the black hole loses energy and approaching it falls into the accretion disk. in which it's torn apart by the tidal forces, heated up due to the frictions and collisions, and approaching the black hole accelerates to a very high speed. And we supposedly observe the radiation of this ionized accelerated gas in broad line regions. After that, the matter falls into a zone with a strong magnetic field, and part of this matter goes into the black hole, and the other part is ejected with a huge speed in the form of jets. And this is a single mechanism for creating jets, both for supermassive black holes and for black holes of stellar masses, in which jets are also observed. But in the case of active nuclei, we see radiation from the gas in the accretion disk, and in the case of stellar mass black holes, this radiation is not. And best of all, the totality of observed data explains the disk wind model. If in the accretion disk gas rotates around the black hole, then in the case of a disk wind, the gas moves from the core towards the edges of the galaxy disk. Exactly with such a wind, this asymmetry will be observed, because when viewed from an angle, which most often happens, we see better the part of the gas that is moving away from us. And the gas moving in our direction partially obstructs the gas and dust in the disk. But in this case, another problem arises. What is the nature of this wind? And if this is not the radiation of accretion disk, then it's not clear where the energy comes from, which accelerates these masses of gas. And in the classical understanding of gravity, this question is justified. But in the theory of moving space, this acceleration is natural. But there is one but. If these streams of matter are in every spiral galaxy, then there must be such radiation in every spiral galaxy too. Yes, it should be so. But we see how the properties of this radiation depend on the viewing angle, that the gas and dust of the disk can block part of this radiation. And the larger the masses of the disk, the more likely it's that this radiation will not break through. And this is confirmed by statistics. The larger the masses of the disk, the more likely is that the galaxy has active nucleus of type 2, that is without radiation with broad line. New equipment and new techniques make it possible to find radiation with a broad emission line where it has not been found before, which led researchers to the idea that active nuclei of type 2 do not exist at all. But this applies to the galaxies with active nuclei. But what about galaxies with ordinary nuclei? Early studies showed that the fraction of active nuclei was less than 10% of all, and the Seyfert galaxies are about 1 or 2% of total number of galaxies. But studies carried out in the 90s showed that the proportion of the galaxies with an active nucleus is close to the half of the number of galaxies, and the share of Seyfert galaxies is about 10% of all galaxies. But keep in mind that these studies are more than 20 years old. And what will research show with new equipment and technologies? But you need to understand that in this case too, a thick disk can hide all the radiation. And here the radiation power is important. The higher the energy of the jets, then correspondingly higher the radiation energy. And the higher the radiation energy, the higher the probability that the signal will break through the disk. How do high energy jets differ from low energy jets? By the speed. Jets with high speed have the form of a bar. That is, high energy jets are jets with a bar. And in this regard, statistics show that among Seyfert galaxies, about 80% are barred galaxies. It turns out, if we choose all the spiral galaxies, then just over 60% of them have a bar. But if we choose all the Seyfert galaxies, then 80% of them are barred. That is, jets with high energy in the form of a bar are more likely that their energy will manifest itself on the surface of the disk. It turns out that it's in Seyfert galaxies either a very thin disk, or the jets is somehow not in the disk, or simply the jet energy is very high. And the study of Seyfert galaxies showed the movement of the jet in the disk. In one of the Stefan Quintet galaxies, which is Seyfert, the direction of the jet coincides or almost coincides with the plane of the disk. And besides, this flow of ionized gas coming out of the core coincides with the direction of the bar, and according to the researchers, is the reason for the presence of ionized gas throughout the disk. In recent years, a lot of evidence has appeared of how gas flows out of the nuclei of the galaxies in the form of jets that coincide with the direction of the bars, and spiral patterns that are created by this gas. In some galaxies, the energy of the jets is small, and it creates a spiral pattern without a bar. Such increased outflow observations are due to the fact that new highly sensitive equipment with high resolution has appeared. But despite the obviousness of this phenomenon for us, researchers must interpret observations through known theoretical models. Therefore, they suggest that sometimes the biconical outflow is located in such way that one of its sides coincides with a disk plane, and, as it were, creates an outflow in the form of a thin jet in the disk plane. But some of the researchers directly suggest that this is not inclined biconical outflow, but a jet moving in the disk. And the narrow line region, which is associated with a very weak jet, is actually a side effect of the motion of the jet in the disk. That is, interaction of the jet with stars and interstellar gas provokes secondary gas flows that move perpendicular to the direction of the jet. And these flows are interpreted as a short vertical jet, and part of these flows, leaving the disk, change direction corresponding to the change in the speed of space. And perhaps this is what traditionally associated with biconical outflows. In one of the galaxies, the researchers observe how a spiral pattern begins near the place where the outflow weakens. In the same work, the researchers say that this outflow in those places where it passes enhances star formation. Jets are very well observed in the disks of nearby young spiral galaxies with a pronounced bar. In one of these galaxies, the researchers found the movement of gas and star clusters in the form of outflow, which also coincides with the direction of the bar. And one of the supposed components of this outflow is located inside the disk. At the same time, biconical outflow models are not suitable for its explanation. This is one of those galaxies in which the outflow masses are several times higher than the rate of star formation. But most often, jets directed into the disk are observed in very young disk galaxies with a very active nucleus. In such galaxies, the outer gaseous disk may be absent or very insignificant. And in one of these galaxies, we see a typical pattern of disk outflow. Also, researchers are trying to interpret it as a biconical outflow. And to explain the movement of gas in the western and eastern part of the galaxy, they suggested the influence of gas kinematics from small satellite galaxies that merge with this galaxy. But the biconical outflow in the northern part should not be redshifted for us. And the southern outflow doesn't have a velocity gradient, which may indicate that this outflow is from the disk. In one of the works, the movement of the jet in the disk, according to the authors, provokes star formation. But these are all disk galaxies, in which the disk hides the movement of the jets. Similar jets of matter should also exist in elliptical galaxies, which gradually create the disk, because the theory of moving space implies that the disk galaxies originate from elliptical spherical, by ejection of matter in rotating jets from the active nucleus. The ejection occurs in the same plane in which the disk appears. Thus, the galaxy is transformed from spherical to elliptical, and after, the disk structure continues to grow, and the galaxy is transformed into a lenticular. And then, if the energy of the jets is not high, the galaxy becomes a spiral flocculent. But if the energy of the jets is high, then we see a clear spiral pattern grand design. And indeed, research shows that there's no clear line between elliptical, lenticular, and spiral galaxies. The division between them is conditional, according to the ratio of the bulge and disk sizes, and other parameters. If we take all these galaxies and distribute them according to these parameters, then we will not see a clear separation into types. Instead, we will see a smooth transition between them, just as it would be if all these species were only different stages of the overall evolution. and this evolution depends on several factors, and therefore various scenarios are possible in it, which we will talk about a little later. According to the kinematics, researchers divide early type galaxies into two subgroups. These are fast rotators and slow rotators. Fast rotators have a more pronounced disk structure, and slow rotators have a less pronounced one. And this is a confirmation of the theory of moving space, which shows that the more massive the disk, the greater the anisotropy of the velocity of space. And in disk galaxies, the speed of space in the plane of the disk is higher, and the greater the speed of space, the stronger the effect of the inertial trap, and the greater the maximum circular speed. And this explains why the velocities of halo and disk stars differ so much. And as I said earlier, there are elliptical galaxies that are almost spherical in shape, and such galaxies are devoid of any ordered movement. That is, they do not have any stellar disk. And the most surprising thing is that outflows in the form of spiral arms are found in such galaxies. That is, if in these galaxies it can be assumed that the stars in the disk create the Lindblad resonance and provoke an increase in gas density and enhance star formation, which leads to the formation of spiral arms. Then, in elliptical galaxies, in which there's no disk and all the movement of stars is chaotic, it's not possible to apply the theory of density waves. But bars and spiral arms from gas are also found in them quite often. A feature of early type galaxies is the disturbed kinematics of gas relative to stars. That is, researchers in them often observe that the axes of rotation of the gaseous and stellar disks do not coincide, and there are cases of counter-rotation of gaseous and stellar disks. But sometimes this difference in kinematics doesn't concern the entire disk, but only the core. These phenomena are called kinematic misalignment and kinematically distinct core. From this kinematic misalignment, it's possible presumably determine the source of the gas. Since the researchers proceed from the hypothesis that gas from an external source can swirl in a random direction, that is, the gas that has remained in the galaxy from early stage of its evolution, or simply has an internal origin, must have the same direction of rotation as the stars, and the gas that accreted from the outside can have any rotation. Based on these estimates, in most of the galaxies, the gas has an internal origin, but the question of the origin of this gas has not yet been resolved. The kinematically distant core in early type galaxies may indicate that the gas around the core has a radial motion rather than a circular one. Also, sometimes it's the core star that moves separately from the rest of the disk. This scenario is also supported by the fact that the gas kinematics often has a radial dependence. That is, if there is a rotating thick gas disk in the galaxy, then the kinematics of outflow manifests itself in the core or on the outskirts, outside of the gaseous disk. Also, statistics show that in fast rotators, a kinematic misalignment and a kinematically distant core are much less common, which is logical, since fast rotators have a more massive disk that better masks the radial movement of the gas, and slow rotators are much more likely to have a kinematic misalignment, which researchers sometimes interpret as a radial dependence of gas kinematics or even gas twisting. But if you look at this velocity field, you will easily recognize the picture that I showed you earlier, which indicates not the twisting of the gas, but the radial outflow of the gas along the disk. A weak kinematic misalignment has been found in most of early type galaxies, and as the researchers note, the kinematics of early type galaxies is more similar to the kinematics of spiral galaxies than to the result of a merger of galaxies predicted by models. In addition, galaxies that show kinematic misalignment often have spirals and bars of gas and dust. The problem of gas kinematics in early type galaxies has no solution, and there is still no explanation of how a gas disk is formed that rotates perpendicular to the stellar disk, or a gas disk that rotates against the stellar disk. To this, studies have not yet answered, and this gas is too rich in metals to be external. But if it's internal, then how does it change its kinematics? The most important result of the research was the discovery of a connection between elliptical, lenticular, and spiral galaxies. And this connecting link is the kinematics of the disk. And common are also the components that were previously considered attributes of spiral galaxies. These are spiral patterns and bars. And direct evidence of outflows in early type galaxies is quite common. And as expected, they are really easier to observe due to the absence of a thick disk. As for the spiral structure itself and the density waves, the simulations fail to reproduce a long-lived spirals. In simulations, they are very unstable. Stable spirals are obtained by simulating solitary galaxies without bars. And at the same time, restrictions on the properties of the spiral and bar appear. But observations show that about 70% of all galaxies are spiral. That is, the reason for the existence of a spiral pattern in galaxies depends very little on any factors. In addition, there is a clear correlation. In large barred galaxies, the spiral is a grand design, and this correlation doesn't even depend on the type of galaxy. In general, more than 60% of spiral galaxies have a bar. In addition, spiral structures and bars, but made of gas, are also found in a significant part of elliptical and lenticular galaxies. That is, if in simulation it's necessary to create special conditions in order to obtain a stable spiral. Moreover, a spiral structure with a bar doesn't obtain at all. Then, in the local universe, most galaxies are spiral, and most of them with bar. From this, we can draw a very logical conclusion. Our understanding of this phenomenon is fundamentally wrong, or the problem of fine-tuning appears again, and the most of the galaxies in the universe become artificial, man-made. In addition, the flocculent patterns in the optical range completely coincide with the flocculent patterns in the infrared range. That is, star formation itself has a fragmentary, flocculent form, which in turn is not very compatible with the theory of density waves, and the share of flocculent galaxies is about 60% of all spiral galaxies. Thus, it turns out that theory of density waves has difficulty in explaining a very large number of spiral galaxies. But the outflow of matter in the form of a jet as the source of this spiral pattern also has difficulties in explaining. And of course, these difficulties appears only in the paradigm of classical theory. You have probably heard that the pattern of a spiral galaxy has a shape according to the Fibonacci sequence, like a snail shell spiral pattern, as well as many other spirals in nature. And yes, it is, but only partially. Only a small part of galaxies have such patterns. Spiral patterns have a varied look. Some are looped, and accordingly they can no longer be called spirals. According to the classical concept of gravity, the outflowing gas from the core of the galaxy under the influence of gravity should lose its speed with distance. Accordingly, all spirals should be with a decrease in distance between the turns. That is, the turns of spirals should be compacted towards the edge of the galaxy. But in the theory of moving space, the speed of movement of matter depends entirely on the speed of space and on whether space is accelerating or slowing down in that place. And therefore, the spiral can have a different pattern. And if the matter is accelerating, then the spiral will be expanding. If the matter is slowed down, then the spiral is closed. And the speed of space is related to the distribution of matter in the galaxy and has some relationship with the rotation curve. This was described in detail in the previous video. Another problem with this interpretation of spiral patterns is the accretion disk model. This model is needed to explain the high-speed jets of quasars, small black holes, neutron stars, and other similar objects. But the model is only capable of explaining the mechanism for supplying matter to the jet-emitting object. But how exactly the acceleration of matter occurs is still questionable. And if we assume that the quasar jets are directed into the disk and rotate in the disk plane, then these jets should blow away the accretion disk. In turn, the absence of an accretion disk means that jets cannot be emitted. For this model to work, it's necessary that the plane of the rotation of the accretion disk be located perpendicular to the plane of the disk of the galaxy and perpendicular to the jets of the quasar. That is, this plane must rotate synchronously with the quasar. That contradicts the law of conservation of angular momentum. But it should be noted that the accretion disk model provides at least some explanation for the fact that the matter flows out of black holes in the jets at near light speed. And if we remove the model of accretion disk, then the researchers have no idea where this matter comes from and how it accelerates to such huge velocities. Also, observations show that the accretion disk model is often unable to explain the observations. There are even observations that cast doubt on such an interpretation of the processes taking place near a black hole. And in general, if we consider the accretion disk and the black hole as a source of the jets in quasars, then why do so few galaxies have jets? We know that the black hole is present at the center of almost every galaxy, and that the core is richest in gases and dust, a place in galaxies. That is, there is a nutriment for a black hole in any nucleus, and there should be an accretion disk near almost every black hole. Why then are there so few galaxies with jets? Everything falls into place if we assume that the spiral patterns are quasar jets directed into the disk, and accordingly spiral galaxies should not have vertical jets. So it is. And this is another unsolved mystery of astrophysics, and it sounds like this. Why are jets of different energies and different sizes quite often observed in elliptical galaxies, while in spiral galaxies jets are observed extremely rarely, and if they are observed, then they are very weak and very short-lived. High-energy jets are extremely rare in spiral galaxies, and more often, not the jets themselves are observed, but their remnants. This phenomenon is called a double-double radio-loud galaxy, which occurs in extremely massive spiral galaxies. Apparently, jets in spiral galaxies sometimes change direction for a short time. That is, they are not emitted to the disk. Galaxies that emit powerful jets are almost always elliptical. Among most massive elliptical galaxies, about 20% have a radio-loud core. And in general, the active core is more often found in early-type galaxies. The larger the ratio of a bulge size to the disk size of a galaxy, the more likely it's to have an active core. And this is in fact one of the indicators that determine the type of galaxy. And this is logical. The more massive and thicker the disk, the more difficult it's to detect the active core. Moreover, there is another very important observation. In galaxies with active nucleus, a younger population, that is, the gas emitted from the active core keeps the stars in a younger state. The probability of having a radio-loud active nucleus increases with the mass of the galaxy. This observation is true primarily for early-type galaxies. That is, in elliptical galaxies, the greater the mass of the galaxy, the more likely it's to have a powerful nucleus. And in spiral galaxies, there is a similar correlation. The faster a galaxy rotates, the more likely it's to have a grand design spiral. The rotation speed is related to the mass of the galaxy by the Tully-Fisher relation. The more massive the galaxy, the faster it rotates. And it turns out that the more massive the galaxy, the higher the probability of having a grand design pattern. And in our interpretation, the grand design pattern indicates a higher energy of the jets, and accordingly, a higher energy of the core. And what else has a correlation with the mass of the galaxy? The mass of the supermassive black hole. And it turns out that the more massive the black hole, the greater the energy of the nucleus. This assumption may seem unreasonable, but there is another correlation confirming this idea. The energy of the outflows has a correlation with the mass of supermassive black hole. There is another factor that we have not yet discussed in detail. This is metallicity. Studies have shown that the metallicity in a galaxy depends mainly on the star formation rate. And this is logical. The faster star formation, the faster stellar evolution, and the faster heavy elements are formed. But we have found out that the high rate of star formation is only a side effect of the activity of the nuclei. The core is the place with the highest metallicity in the galaxy, and its metallicity depends on the luminosity of the nucleus. And the luminosity of the nucleus directly depends on the mass of the black hole. And this correlation of metallicity and the mass of black hole has not changed for more than 12 billion years. And it turns out that the metallicity of the galaxy depends on the mass of supermassive black hole. The outflow of the high metallicity gas from the core also explains the mystery of the high metallicity of gas in polar rings and counter-rotating gas disks. The metallicity of these gas rings and disks is higher than in the rest of the galaxy, which indicates that this gas is coming from the core, and this in turn proves the radial outflow of gas in some cases of kinematic misalignment and kinematically distinct core. In some cases, the gaseous outflow in the form of a bar can be interpreted as a gaseous circumnuclear disk. Therefore, it's possible that part of the circumnuclear gaseous disks is actually an outflow from the nucleus. And if the main source of heavy elements in the galactic gas is a supermassive black hole in the center of the galaxy, and this gas is carried by jets throughout the disk and mixed into the stars of the disk, then the problem of G-dwarfs is solved, and it becomes clear how G-dwarfs in our galaxy have the same level of metallicity. And you might think that maybe G-dwarf problem has some other explanation, and it's possible that this is not due to the influence of jets of gas. But I haven't told you one important detail yet. The fact is that the problem of equal metallicity is not limited to G-dwarfs. Just using the example of G-dwarfs, we can presumably see the evolution of metallicity. In general, the problem of equal metallicity extends to all the stars of thin disk, and exactly in this region that the jets rotate. If such flows of gases occur in every spiral galaxy, then something similar should occur in our galaxy, because our galaxy apparently is also spiral. Our galaxy contains clouds of both ionized and cold gas, the main feature of which is their very high radial velocity. Some of these clouds lie in the plane of the disk of galaxy and can be associated with spiral arms. And in the center of our galaxy, there is a huge accumulation of molecular gas, which is called the central molecular zone. And this cloud of gas is expanding radially, with a speed of up to 150 km per second. The radial moment of this gas is several times higher than the total radial moment that could be obtained from the wind of all massive stars in the central region. That is, the stellar wind cannot be the cause of the movement of this gas. The source of energy cannot be a supernova explosion. The researchers suggest that this ejection is most likely associated with the activity of supermassive black hole in the center of our galaxy. And the event that produced this outburst happened about 600,000 years ago. A characteristic property of active nuclei is the unpredictable variability of their radiation. You have probably heard that the quasar jets can change their intensity by orders of magnitude in a very short time. A similar variability is inherent in the radiation of broadline in Seyfert galaxies. But the most interesting thing is that the radiation of supermassive black hole in our galaxy has exactly the same property. That is, the emission of jets by quasars has a high variability. In Seyfert galaxies, we see a broad emission line in the radiation spectrum of nucleus, and this radiation also has a high variability. And the study of Seyfert galaxies showed the presence of jets in the plane of the disk. The radiation in the center of our galaxy also has a high variability, but we do not see the jets directly, but we see a cloud of expanding gas in the center of our galaxy. And this jet variability creates an intermittent gas flow, which is expressed in intermittent spiral pattern. That is, active cores with variable jet energy create an intermittent gas flow that looks like a flocculent pattern. And now let's talk about the evolution of galaxies, about how galaxies of different types are formed. It all starts with small elliptical galaxies of small ellipticity, that is from almost spherical galaxies. It is this type of galaxy that is most likely to arise as a result of the collapse of a protogalactic gas cloud. A black hole forms in the center of this galaxy, which eventually gains mass. At a certain point, matter begins to form in its immediate vicinity. Perhaps such an idea sounds extremely fantastic, because matter cannot be formed from nothing. However, during the birth of the universe, matter was formed from something. And we know about the some equivalence of mass and energy. Nevertheless, somehow as a result of the collision of gamma quanta, an electron and a positron are formed. How exactly and why matter can be created in the vicinity of a black hole, we will talk in another video. This matter leaves the vicinity of a black hole and accordingly accelerates to a very high speed, because it leaves the zone close to the event horizon, where the speed of space is close to the speed of light. This matter, in the form of jets, under the influence of some effects, eventually create first a gas disk and then a stellar disk. Gradually, the disk grows and begins to mask the active core. Therefore, in more massive disks, it's less likely to detect an active nucleus with a broad emission line. As the disk grows, the galaxy transforms first into an elliptical galaxy with a high ellipticity, and later into a lenticular galaxy, in which the pattern has the form of a ring or a weakly pronounced spiral. And if the spiral is clearly visible, then the galaxy is a spiral. Over time, jet energy increases, and the galaxy turns into a spiral grand design. Thus, the mass of the galaxy can continue to grow, and the galaxy becomes a giant massive spiral. If the jets begin to rotate not in the plane of the disk, but in a perpendicular plane, then gas is present in the disk, but the effect of quasi-star formation stops. The stars in the disk quickly burn out their hydrogen and take on their true age. Therefore, stars in lenticular galaxies are often over 10 billion years old. Gradually, the rotating jets form a gaseous polar disk or ring. If the jets do not rotate in the same plane or precession occurs, then a gas ring cannot form, but at the same time, bulge stars get new gas and get younger. Therefore, bulge stars in lenticular galaxies are often younger than disk stars. And precessing jets are sometimes found in the universe. In this case, there is no violation of the laws of physics in changing the direction of rotation of jets, since the direction of jets is not carried out by the physical rotation of the black hole, and it's performed by the configuration of magnetic field surrounding it. Because such jet reorientations happen in galaxies, and these cases are of great interest to researchers, because the reorientation happens very quickly, without intermediate position. And this, in turn, also contradicts the accretion disk model. There are galaxies in the universe that have polar rings formed, and there are galaxies in which, according to researchers, these rings are forming. And in these galaxies, a gas pattern in the form of a spiral has been discovered. And in one of these galaxies, the kinematics of this gas was measured. And it turned out that this is the same outflow pattern in the form of rotating jets. Lenticular galaxies are more common in clusters of galaxies. Their increased abundance can be explained by the fact that the magnetic field that controls the direction of jets interact with the magnetic fields of other galaxies, and therefore either change direction or stop the emission of matter. And if the jets simply change direction of rotation to the opposite, then in the stellar disk, a gas disk is formed over time, which rotates in the opposite direction to the stellar disk. Options with a tilted gas disk are also possible, but such disks are not very stable. A scenario is possible when the central black hole leaves the galaxy. This can happen as a result of several reasons. As a result, star formation almost completely stops in the galaxy, despite the presence of gas in it, and the galaxy exists in such a state until a new black hole forms in it. if a similar scenario occurs in a very massive spiral galaxy and the new black hole emits low energy jets, then this galaxy becomes a giant spiral galaxy with low surface brightness. Also, it's more likely that such galaxies originate from ordinary spiral galaxies, which have a black hole of medium or low mass. And if the growth rate of the mass of this black hole is not high, then, for many billions of years, it will be able to create a giant disk with low brightness. And this is probably the most plausible scenario. And the growth rate of the mass of black holes is really not so great, because in the universe we see that in small galaxies, young stars, and the energy of black hole is enough to keep stars young. And in the most massive galaxies, almost always old stars. And if the growth rate of the mass of galaxies and black holes were comparable, then the stars in giant galaxies would be younger. That is, such a scenario not only explains the evolution of giant spiral galaxies with low surface brightness, but also explains the observed bimodality of the properties of galaxies. Maybe there is some limit to the mass of black hole at which it stops emitting jets, or there is some mechanism for weakening the activity of the nucleus with an increase in the mass of the black hole. If a giant spiral galaxy has a very heavy and powerful black hole, then slowly these powerful jets will dynamically heat up the disk. The disk structure will be destroyed, and the galaxy will become a giant elliptical. And a very small proportion of a spiral galaxies among super heavy galaxies confirms the likelihood of this scenario. And jets that are not capable to destroy the disk structure are not capable of keeping the stars of the giant massive disk young and bright. In other words, jets that are too strong destroy the disk, and the spiral galaxy becomes elliptical. And the jets with less energy are not able to keep the massive disk bright, and galaxy fades. Surely there is a golden mean, and some of the giant spiral galaxies still retain a thin disk and are not faint. But the greater the mass of the galaxy, the smaller the fraction of such galaxies. And if in massive spiral galaxies the energy of these jets is not enough to maintain the brightness of the disk, then in the case of massive elliptical galaxies, the situation is even more complicated, because the stars in them are not as densely located as in the disk of spiral galaxies. And this partly explains why, on average, elliptical galaxies in almost all masses have older stars, and they themselves are less bright. Also, if there are any conditions under which a black hole ceases to generate jets, then for sure this is what happens most often in elliptical galaxies, because they often have no young stars at all. It's quite possible that at one moment there is a reorientation or even stacking of the jets, since it's not completely known how and why short-term changes in the direction of the jets occur, and the reasons for their rotation are also unknown. Therefore, this option is not excluded. And if the jets get stuck, the disk will eventually be destroyed, and the galaxy will be transformed into elliptical triaxial galaxy. But triaxial elliptical galaxies can form in other ways, as well as mergers. Statistics show that quasars have the most powerful jets, and these are static jets. And almost always the host of this quasar is a giant elliptical galaxy. And according to the statistics, the most massive are elliptical galaxies. Spiral galaxies dominate in the middle masses. Therefore, the final result of evolution of a spiral galaxy is the most likely an elliptical galaxy. And if the jets are controlled by the magnetic field, then perhaps this field is not always with two poles. And this could explain the multi-arm pattern of spiral galaxies. And short-term reconfigurations of the field would explain short-term jets directed perpendicular to the disk of the galaxy. That is, it's possible that in spiral galaxies, during the appearance of the jets perpendicular to the plane of the disk, the jets in the disk do not disappear. The initial galaxies from which everything begins can have different masses and sizes. Therefore, there are spiral galaxies with a large bulge, and there are spiral galaxies almost without bulge. If the jets rotate with precession or even chaotically, then an elliptical galaxy may never create a disk, will continue to gain mass and remain elliptical. If anyone has any doubts that supermassive black hole is capable to leaving the galaxy, then researchers have already found signs of a supermassive black hole not being in the center of the galaxy. And recently an object was discovered behind which a trail of newborn stars stretches. This object has been interpreted as a supermassive black hole. Such a wandering black hole can create a new galaxy around itself, and blue compact dwarfs are the best contenders for this role. The energy of their radiation is sometimes comparable to the energy of quasars, and their star formation rates are also quite impressive. And apparently, such a scenario is not uncommon, because there are dwarf galaxies with black hole masses tens and hundreds of times more massive than a black hole in our galaxy. At the same time, the mass of stars in these galaxies is tens and hundreds of times less than the mass of stars in our galaxy. And the probability that such heavy black holes form in such low-mass dwarf galaxies is very small. But the probability that a giant black hole will create a galaxy around itself is much higher. Often, a broad line emission is observed in such galaxies, which indicates the high-speed movement of gases, possibly outflows. It seems that the high-energy jets in dwarf galaxies do not allow gas to accumulate. But at the same time, in such galaxies, there are young stars and a high rate of star formation, while the galaxy itself has not reached the minimum concentration of gas for star formation. This is what the evolution of galaxies looks like from the point of view of theory of moving space. But this is only a basis to which many other scenarios can be added, because as you can see, there are many factors that influence the evolution of galaxies. For example, I have not taken into account the rotation speed of the quasar, on which a lot also depends. Of course, this evolution can be adapted to the classical theory, but in this case it's necessary to invent a mechanism for accelerating the jets, because the model of the accretion disk in this case will no longer be applicable. An accretion disk probably exists at all, and probably the matter in it accelerates to high speeds. But it's definitely not responsible for the presence of jets in quasars. Otherwise, such jets should have been presented in probably half of the galaxies in the universe. In addition, recent observations suggest that there's no strong connection between the absorption of matter by the black hole and the emission of jets by it. Jets have low-mass black holes, neutron stars, and other similar objects, but there's no radiation from the matter supposedly moving in the accretion disk. Or maybe there's no accretion disk in these objects at all, and the flowing jets are the result of completely different physical processes. Such a vision of the evolution of galaxies implies a constant increase in the mass of the matter in the universe, because in this interpretation, a new matter is formed in the nuclei of galaxies. And the classical cosmology implies that the amount of matter in the universe doesn't change. If you remember, at the beginning I said that the simulations do not reproduce the galaxies that we see in the universe, about the fact that in simulations huge rates of star formation and very heavy galaxies are obtained. And the situation is complicated by the fact that research reveals that the content and distribution of molecular hydrogen in galaxies the last 12 billion years almost doesn't change, and the last 10 billion years it doesn't change at all. That is, galaxies 12 billion years ago already look almost the same as today's galaxies. Especially precisely, this distribution of hydrogen coincides in the faint part, which in the near universe corresponds to the edges of the disks. Also, lambda CDM cosmology implies that at this early time, galaxies are only clumps of gas, which only occasionally resemble disk morphology. Roughly speaking, studies suggest that the amount of hydrogen in galaxies has not changed over the last 10 billion years. But at the same time, star formation occurs, and accordingly, the gas must be consumed. Therefore, such inflow of gas is needed, which, on the one hand, must cover the gas consumption for star formation, and on the other hand, this gas must come at such a speed that its distribution in galaxies would be preserved. Moreover, it should come mainly to small and medium-sized galaxies. And one of the researchers' conclusions sounds like this, that everything looks as if hydrogen for many billions of years comes from some external reservoir. Because if all the hydrogen is involved in the simulations at once, then we get huge rates of star formation and very heavy galaxies. And if hydrogen comes in slowly from some hypothetical external reservoir, then the rate of star formation will return to the normal, because the smaller the starting matter, the less massive galaxies will appear. And here you need to understand one important thing, that this hypothetical reservoir cannot be intergalactic space, since most of the primordial gas in the early age formed protogalactic clouds, which later formed galaxies. Therefore, there should not be a significant amount of free gas in intergalactic space. And now, think about what kind of reservoir it could be, which would help prevent the gravitational collapse of all matter into the first galaxies. I know that one might now think of hypothetical parallel universes or hypothetical white holes. But let's talk within the framework of real physics and not science fiction. I think there's no reservoir. So much matter didn't exist at the early age of the universe. It was produced gradually in the active nuclei of galaxies. And the universality of the distribution function of hydrogen in galaxies is a confirmation of the theory of moving space. It confirms the relationship between the distribution of matter in the galaxy and the speed of space, the relationship between alpha and beta functions. And the outflowing matter from the core of the galaxy is distributed in such a way that a constant speed of space would be obtained throughout the entire disk. That's why any galaxy in its evolution tends to have a flat rotation curve throughout the entire disk and even far beyond it. This was discussed in the last video. And perhaps this explanation sounds a little fantastic, because the amount of matter in the universe cannot increase. But research shows that maybe that's exactly what happens, because the number of heavy and very heavy galaxies per cubic megaparsec has changed very little over the past 10 billion years. But keep in mind that the universe has been expanding all this time. But what is most interesting is that the number of very heavy galaxies in the early universe exceeds the number predicted by simulations by 3 orders of magnitude. That is, there are thousands of times more heavy galaxies in the early universe than models predict. Therefore, the next time you heard that the lambda CDM cosmology is in good agreement with observations, you will know that it's not. Of course, this study is old, and in the near future, data on the ultra-distant galaxies will be replenished thanks to new telescopes. And when there will be more complete and detailed research on this topic, I will return to it. But even preliminary results suggest that we need to revise the cosmological models. And if you still have doubts that jets of matter from active nuclei can imitate star formation, then there is an interesting discovery for you. In the center of the Milky Way, in the immediate vicinity of a supermassive black hole, a newborn star has been found. According to the researchers, a star cannot form there, because the conditions there are extremely unfavorable for this. But what if this star didn't form there, but just got a portion of fresh gas and became like a young star? There is also an interesting study about what would happen to our planet if it fell under the action of the galactic wind. And the consequences of such an event would be catastrophic. But our solar system is supposedly located at the distance of the rotation radius. This is the distance at which the stars rotate around the center of the galaxy synchronously with the spiral pattern. Therefore, the probability that the solar system will fall into the jet of this wind is not so great. Is it just a coincidence that we, as a biological life, appeared precisely near the rotation radius? Maybe it's just a coincidence, but the idea is not without logic, that the probability of the emergence of life in the region of the rotation radius is higher than in other regions of the galaxy. But nevertheless, mass extinctions in our planet are periodic, And one of the possible reasons for the periodicity of mass extinctions is the passage through the spiral arms. When I almost finished preparing the material for this video, information has appeared that in one of the binary systems, this is the name given to massive objects such as a black hole or neutron star and a companion star, in which the gas from a companion star gradually flows and accretes into a compact massive object. In this binary system, this so-called accretion disk has a disk wind. And this discovery should shed light on how a supermassive black hole forms an entire galaxy. And in order to rethink this, a theoretical paradigm shift is needed. But this will not happen until alternative theoretical basis for creating new models appears. And this basis can be the theory of moving space. And when I had almost finished editing this video, the news came out that radio telescopes had found hundreds of filaments supposedly flowing from a black hole in our galaxy. And for researchers, this discovery came as a real surprise. It seems that the revolution in cosmology and astrophysics is really very close. And what do you think? Is the spiral structure formed by density waves or jets from the nuclei? Please share your opinion in the comments.